Hi all, welcome to Sidza.com. Now in this video we will learn about the close packing in the crystalline solids. As we know that crystalline solids generally have a very high density because the particles, the constituent particles of the crystalline solids are very closely packed together and a very small amount of space is left as empty in between atoms. Okay, so in a crystalline solid, atoms are closely packed. That's why they have a maximum density. Now, to understand the close packing in the crystalline solids, we can consider the constituent particles of a crystalline solids as hard ciphers of identical size. And as we know, a crystalline solid has a three-dimensional structure. To understand the close packing, to understand the pattern in which the atoms are actually arranged in a crystalline solid, we can break up this particular topic into three main headings, right? So number one will be the close packing in one dimension, close packing in two dimension, and the close packing in three dimension. That means we will see what is the arrangement, how the atoms are actually present in one dimension, and then two dimension, and in the three dimension, right? Now let's start with the one dimension. This is pretty simple. When atoms come close, right, they'll form a one row of an atom, one row of atoms. Okay, so in a one-dimensional close packing, each atom is in contact with the two other atoms, right? So that means in a one-dimensional close packing, the coordination number will be 2, right? So here you can see a particular atom, it is in contact with two other atoms, right? So there are two atoms touching this particular atom in a one dimension. So that means the coordination number is 2, and this is pretty simple. Now let's go to the two-dimensional close packing. When you have a one row of an atom, and when these different rows of atoms, right, form a plane, what kind of a geometry we can have? How these rows of atoms can form a one layer of atom, one plane of atom, right? There are actually two ways of doing that. So that means in a two-dimensional close packing, we find there are two types of arrangement. One is called as a square close packing, the other one is a hexagonal close packing. This one is a square close packing, and this one is hexagonal close packing. You can see here, this is a square close packing, and why it is called a square close packing is because if you look at this particular atom, now this particular atom is in contact with the four other atoms, right? So that means there are four other atoms touching this particular atom. So that means the coordination number here is 4, right? For this atom, there are 4 atoms adjacent to it. So that means the coordination number is 4. And when you join the centers of these 4 atoms surrounding a particular atom, what do you get? You get a square. That's why this is called the square close packing. Over here, if you look at this one, the particular atom, it is surrounded by the 6 adjacent atoms. There are 6 atoms touching it, right? And when you join those centers, right, when you join the centers, what do you get? You get a hexagon. Okay, you get a hexagonal shape. That's why this is called the hexagonal close packing, right? And here the coordination number is 6 because each atom is surrounded by the 6 atoms. So that's why the coordination number is 6. And next point, just looking at the two diagrams, you can easily find out that we find there is more empty space here, more empty space is there in square close packing than in the hexagonal. In the hexagonal also we find some empty space, but that empty space is very less, right? So that means hexagonal close packing in a two dimension is more efficient than square close packing, right? So that's why in a square close packing the efficiency is 54.2, the packing efficiency is 54.2, and the space which is left as an empty will be 100 minus 54.2%, right? And here the atoms actually occupy how much of space? 60.4%, right? So 60.4% of the available space is occupied by the atoms, and only 100 minus 60.4 that is left as an empty space. Now let us discuss the close packing in 3 dimensions. If you have a one layer of an atom, as we discussed in a square close packing, suppose you have a square close packing in a 2 dimension, right? This is a square close packing in 2 dimension, and you got a one layer of atoms. Now if you want to put a second layer of atoms on top of the first layer, exactly on top of the first layer, like this, okay? So that means the arrangement in the first layer will be similar to the arrangement in the second layer. And if you put the third layer having the the pattern exactly similar to the second, you get this one, right? So by this way you get an entire crystal, you get a three-dimensional crystal. And you see here in each and every layer the arrangement is same. So that's why this is called as an AA type of arrangement, right? This is called as an AA type of arrangement. Okay. And from this one, what will be the unit cell of such a crystalline solid? We have discussed previously what a unit cell is and what are the different types of unit cells. Now let's see here. If I join these four atoms here, right? And if I take four more adjacent atoms to it, this one, this one, this one, and this one, right? Let's join those four atoms also. What kind of a geometry you get? Isn't like this? Okay, that means the unit cell from such a crystal will be a primitive unit cell, and we know the primitive unit cell is the one where you find atoms only at the corners, right? Only at the corners. Okay. This type of an arrangement, it's called square close packing in 3 dimensions, and from square close packing, we get an AA type of a lattice, and the unit cell will be a simple or a primitive cubic lattice. Now what about the hexagonal close packing? If you have a hexagonal close packing in 2 dimensions, you got suppose a one layer of atoms, right? And the arrangement in this particular layer is a hexagonal close packing. Now suppose if I want to put a second layer of atoms on top of the first, such that the atoms in the second layer occupy these voids, okay? So that means if this is the arrangement A here, in the second layer, right, the arrangement is different. Let's go back here and just check it. Say I want to put the atom over here, right, on this void. And when you do that, that means the arrangement in the second layer is different than the first layer. It's not similar to the the first layer, right? It's different. And these voids are not occupied, only some voids are occupied, right? This void is occupied, this is left, and such, this is occupied, this is left, right? Like that. And now let's have a third layer of atoms such that the arrangement in the third layer is exactly similar to the first one, right? So I'll put a third layer with the arrangement similar to the first layer. So this is the third layer of an atom having arrangement A. And the arrangement that you get here is called as an AB type of arrangement, right? Okay, this is an AB type of an arrangement. And the unit cell that you get from here, see, we have an arrangement A in the first layer, second layer is different, the third layer is similar to the first one, right? So from AB type of arrangement, what do you get? You get a hexagonal close packing, right? This is the unit cell from a hexagonal close packing in 3-dimensional crystal. Now, another arrangement that you normally see in the crystalline solids is, suppose you got a hexagonal close packing in 2 dimensions, you have a one layer of atoms here and the arrangement A, and now I'll do the same thing, I'll repeat the same thing, on the second layer. If I take a second layer on top of these voids here, that means the arrangement in the second layer is different as discussed previously. Now what I do, I'll not take the third layer with a similar arrangement to this first one, rather I'll take a third layer on these voids. Let's put the atoms in the third layers on these voids, okay? Now I want to occupy these voids. So what will happen now? The arrangement in the third layer is totally different than A or the B, than the first layer and the second layer. That means the third layer has a different arrangement. It doesn't resemble with the first layer or the second layer. And if I take fourth layer of atoms and that has a similar arrangement to the first one, right? Fourth layer of an atom, it has a similar arrangement, right, to the first one. then I can say, you know, the arrangement that you got here will be called as an ABC type of an arrangement, right? Like this. Okay, so this is a cubic close packing. Why? Because the unit cell that you get, see, this is the arrangement A, this is the B, this is C, this is A, and over here, what do you get? You get a unit cell which is called as a face center, right? You get a face centered cubic unit cell from this type of an arrangement here, right? So you have an atom at the corners, and in addition to the corners, you have atoms at each face, right? So this is the one face, second, third, 4, 5, and 6, and we know there are 6 faces for any cubical structure. So this is called as a cubic close packing, and in the cubic close packing, the arrangement is ABC type. So far what we learned, we have learned that a crystalline solid in a 3 dimension can have, number one, it can have an AB, it can have an AA type of an arrangement, right? Okay, and the unit cell normally that you get is a simple unit cell, right? It is a simple, or you can say a primitive unit cell. Then from hexagonal close packing in the 2 dimension, from that, you know, layer of atoms, you can have 2 arrangements. One is called as an AB type of an arrangement, right? And from that, what you get a hexagonal close packing, HCP, and the third one is ABC type of an arrangement, right? And you get a CCP, cubic close packing arrangement, right? Hope you got the concept. Thanks for watching the video. Bye for now.